In this video, we are going to take a look at Maxwell's derivation of the normal distribution. So this gives you one reason of why we suddenly considered the normal density in this weird form as we have it. Now, James Clerk Maxwell, the eminent physicist, arrived at this normal distribution using some very simple assumptions and brilliant logical manipulations. So he was working with a gas. So here you see the different molecules. It is floating in space. Certain molecules are closer to us, they are looking big. Some are far away, they are looking like tiny dots. Now all these molecules are moving all over the space. Now if at a certain time point you take a snapshot, as I have done, with all the velocities shown up as arrows, in that case, you will find some of the arrows are short, some of the arrows are long, and they are in all possible different directions. Because these are all vectors in R3, some are short, some are long. Now, Maxwell wanted to know the distribution of these arrows. Now, he is thinking of it in the following way. Suppose I pick up one of these molecules at random and look at its velocity vector. In that case, that velocity vector is random. In the same way, if I pick one random person from a population and measure his or her height, then that height is a random variable because the person I have picked randomly. Similarly, the velocity vector at a certain time instant of a randomly selected molecule is a random vector. And suppose this random vector I denote by this vector notation V. In order to study its distribution, I would naturally, or Maxwell naturally did the obvious thing, fixed up some coordinate space in R3, X, Y, and Z, they are orthogonal unit vectors, etc., and expressed this V in terms of the various components, V1, V2, and V3. So all these things are real valued random variables. So his interest was in the distribution of these things, the joint distribution of V1, V2, V3. Now, first of all, it is clear that all these things can take value in R, entire R, positive or negative. Now, here he made his first assumption. That assumption was that all these things are continuous random variables, and not only that, they have got densities. So let Vi have density Fi, I, 1, 2, 3. Now let us understand what can I say about Fi. He is assuming that this gas does not have any overall flow. So though some molecules are moving in this direction, some in that direction, there is no overall flow. So it is not that most of the molecules are moving in a certain direction. If that is the case, then there is no reason to choose one direction preferably over any other direction, which naturally means whatever you can say along the X direction can be said along the Y direction and can be said along the Z direction. Because these three directions are chosen by us, the physicists, completely arbitrarily. The molecules obviously do not know about these things. As a result, we conclude that all the VIs must have the same density. We can drop the subscript I from here. Next, observe that all these directions are mutually perpendicular. As a result, V1 gives the component of V along this vector and V2 gives along a perpendicular vector. So V1 and V2, if you consider them as vectors along this direction and that direction, they do not have any common component. So the component of the V1 part along Y is 0. The component of V2 along X is 0. And also, is there any reason to believe that if the velocity is high along the X component, then the velocity must also be high along the Y component? No, because if that is the case, then you are basically assuming that the flow is more along the 45-degree line. Whenever this is high, this also becomes high. So you are favoring the 45-degree line. But as we have said, no direction is favored over any other, and they are not sharing any common component. As a result, we have VIs are independent. So just by logical reasoning, obviously Maxwell had no way of grabbing a molecule and then measuring and then concluding this. Just by logical reasoning, he concludes that if there is no overall flow, then all the VIs must have the same density and they must be independent. As a result, their joint density must be product of the individual densities. So this must be the joint density of the V vector. Okay, now let's do again some logical reasoning. Suppose I tell you that the speed of a molecule is something, say 3 meters per second. Just based on that, can you say in which direction the molecule is traveling at present? Of course not, because all the directions are just equally likely. So this joint density should not have anything to do with the direction. It should only matter what the speed is. It is quite possible that 30 meters per second is less likely than 3 meters per second, but you cannot make any such comparative statement in terms of the direction. And now Maxwell's brilliance, he just noticed that this is equivalent to the condition that this product must be a function of only the norm of V. That is, this must be a function of V1 square plus V2 square plus V3 square for some function G. He does not know what F is. F is what he is interested in to find. And G is something whose existence he can guess, but he doesn't care what G is. So F must be one such function such that whenever you write this, and this holds for all V1, V2, V3 in R, the product must be a function of V1 square plus V2 square plus V3 square. Well, now we just have to do some mathematical manipulation for which he assumed, like any true blue physicist, that F is differentiable. So differing both sides with respect to V1, keeping V2 and V3 fixed, I get F prime V1, derivative of F. These two things remain unaltered. Chain rule, G prime, this norm square times derivative of V1 square, that is 2V1. Now I can do the same thing with respect to V2 to get FV1, F prime V2, FV3, very much similar to the last one except that I have 2V2. Now remember, he does not care about this G, all that he cares about is F. Now this gives him a good opportunity to get rid of this G, which is present as G prime here, to get, I am expressing this in terms of the F, so it is F prime V1, this divided by 2V1. I will do the same manipulation to this one. So now I have an equality involving F only. Now I have some obvious cancellation, this and these are cancelled. Now remember that this held for all V1, V2, V3. So this will also hold for all V1, V2. Well, there is no V3. Now you may be wondering why I did not repeat the same process for V3 also. The reason is I will not get anything extra. Okay, now that we have this, just observe that this is equal to that and cancel the 2's off. Now take all the V1 quantities on one side and the V2 quantities on the other side to get F prime V1 divided by F V1 by V1 and V1 equals F prime V2 divided by F V2 V2, and this must hold for all V1 V2. Now what does they tell you? Both the things are exactly the same thing, but I have evaluated it at different points. Whatever points I evaluate it at, I'll get the same answer, which naturally means that this must be a constant. Let's call it K. So let's drop the subscripts now. Now I know F must be a function such that F prime V by F V by V is actually free of V. So now we have a differential equation which we can solve in a moment. By taking this V onto that side, once I integrate it, I can immediately get log of FV. No problem taking log, we are working with density, so positive. And this will be K by 2V square plus some constant. And that means FV must be some constant times, so proportional to e to the power kV square by 2. So that basically means it's a density which has this form, e to the power a constant times v square, and that immediately forces F to be a normal density. So starting from absolutely basic assumptions, about the molecules, simply by doing some logical reasoning, Maxwell showed that each of the components must have a normal distribution. Now, in case you are still wondering how did I arrive at normal from this, let's solve the exercise that is coming up. In this exercise, I am starting with the same f, except that I have written the dummy variable as x, some constant a times e to the power kx squared, x in R. I tell you that this is the density. First, you have to argue that k must be strictly negative. You can easily see k cannot be equal to 0 because otherwise it will be just a constant a over the entire R, so the total area under it will be infinite. Obviously, k cannot be greater than 0, then it will be also infinite, so k has to be less than 0. Now, just integrate and make it equal to 1, from which you can work out capital A, and from this you conclude that f is a normal mu sigma square density, and find mu and sigma square, for which you will have this. So mu and sigma square will be obtained as functions of k.